Okay, so having seen the fact that the Gaussian integers form a Euclidean ring and having gone through an elementary number theoretic lemma, we are now focusing our attention on the prime numbers, about which we are going to state something and then we will prove that. Specifically, we are going to look at the odd prime numbers. So let's just see the first few odd primes. So they go like this. Okay. Now if we divide each one of them by 4, then what is the remainder? Let us look at that. This, for example, itself is the remainder when we divide it by 4. This, if we divide by 4, it leaves the remainder 1. This, if you divide by 4, it leaves the remainder 3. This one, if you divide by 4, then it leaves remainder 3 again. What about 13? It leaves remainder 1. So you can see that no matter how many primes you see, how many odd primes you see like this, you will always have either remainder 3 or 1. What is the reason for that? You see, when we divide an integer by 4, the remainder is either 0 or 1 or 2 or 3. These 4 possibilities are there. In other words, any integer is either of the form 4n or 4n plus 1 or 4n plus 2 or 4n plus 3. Now of course no number of the form 4n can be a prime, so this does not appear anywhere in the list of primes. If we want 4n plus 2 to be a prime, then keeping in mind that this can be factorized like this, 2 times 2n plus 1, it will be prime if and only if this factor is 1, because this factor is already greater than 1. So this has to be 1, and that is possible in only one case, when n is 0, and when that happens the number becomes 2. So 2 is the only prime of the form 4n plus 2, which is also the only even prime. Besides this, whatever odd primes we come across, they are either of the form 4n plus 1 or 4n plus 3. Now our ultimate aim in this section is to prove that every prime of the form 4n plus 1 can be written as a sum of two squares of integers. That's what we want to prove. So in that direction, we next state again a small number theoretic lemma. This will be useful in our actual proof. Okay, so by the way, if you are curious about that statement that every prime of this form can be written as a sum of two squares, you can see, for example, 5 is a prime of this form. It can be written as 2 square plus 1 square. Okay, then 13 is also a number of that form. For that also there will be an expression which will be a sum of two squares. Yes, this can be written as 2 square plus 3 square, like that. And there is one more result also, if I am remembering correctly. no prime of the form 4n plus 3 is a sum of two squares. That is also there, however we are not interested in that. So here let P be a prime of the form 4n plus 1. This is not the ultimate result, this is just a lemma. Then the congruence x square congruent to minus 1 mod p has a solution. That is, there is an integer x for which this congruence will be solvable. That's what we want to prove. And the proof is a direct proof. We will produce an actual x and show that that particular x solves this congruence. Let x be this quantity, this product. 1, 2, 3 like that. You take all the factors up to p minus 1 divided by 2. Now note that since p is of this form 4n plus 1, so p minus 1 divided by 2 is not only an integer but it's an even integer. Okay, so this product is actually a product of integers, and as such x itself is an integer. Since p is of the form 4n plus 1, x is a product of an even number of integers. Okay, hence because x is like that, so we can bring a minus sign to every factor without affecting the value of x. It's like having like this, say x equal to 1, 2, 3, 4. Here there are there are an even number of factors, so in place of this we can write minus 1, minus 2, minus 3, minus 4, because of that evenness. So the exact thing we are now going to write here in the general case. So x is minus 1, minus 2, etc. to minus of p minus 1 divided by 2. Now if we try to calculate x square, x square can be, x square is actually x times x. For one of that one of those two x's we are going to use this expression, and for the other x we are going to use this expression. So we can write this product like this: 1, 2, etc. to p minus 1 by 2 times minus 1, minus 2, etc. Let me write here minus p minus 1 by 2. Okay, so x square can be written like this. Since minus k is congruent to p minus k mod p for any integer k, we have this is easy to see. If you take the difference of these two, then you have either p or minus p, which is divisible by p, so that's why this congruence is true. So now congruence modulo p, these negative factors can be replaced by a corresponding term that looks like this, each one of them. So we have I need some ink. Okay, so x square equals this product 1 to p minus 1 times minus 1 minus 2 etc. Now this thing is congruent to 1 times 2 times 3 etc. up to p minus 1 by 2 times. In place of minus 1 we can write p minus 1. For 2 we write p minus 2, and like that all the way up to this. This becomes p plus 1 by 2. Now note that if we change the order of these factors, then we can write this whole product slightly differently like this: p minus 1 by 2. Then we write this one, and we write all the things in the opposite order: p plus 1 by 2 up to p minus 2 and then p minus 1. And this, if you look carefully, this is nothing but p minus 1 by 2 plus 1. Okay, this factor. So this whole product is nothing but p minus 1 factorial mod p, because this, after this equality we are writing congruences, so these congruences are modulo p. Now by Wilson's theorem, p minus 1, okay, let me write it there. Wilson's theorem says that p minus 1 factorial is congruent to minus 1 mod p. So we started our calculation with x square, hence x square is congruent to minus 1 mod p. So that particular value of x actually solves this congruence, and that completes the proof. We can give a small illustration of this result with an example. To illustrate the above result, take p equal to 13. 13 is a prime of the form 4n plus 1 because it is 4 times 3 plus 1. Okay. Then x, okay, what will x be in this particular case? We have to start from 1 and we will end at 13 minus 1 divided by 2, that is 6. So x is 1, 2, 3, 4, 5, 6. If you calculate, this becomes 720, which turns out to be congruent to 5 mod 13, because you can verify that if you subtract 5 from 720, the result is divisible by 13. Note that five square is congruent to minus 1 mod 13. 5 square is 25, 25 plus 1 is 26, which is divisible by 13, so it is true. It has to be true because we have proved the result. And now we come to our final result of this section, that is theorem 382, and it's due to Fermat. And the result is just this: if p is a prime number of the form 4n plus 1, then there exist integers a and b such that p is equal to a square plus b square. This is the result, and we are now going to prove this. And in the proof, we will immediately use what we have proved here in the previous lemma. Since p is of the form 4n plus 1, lemma 382 implies that there exists an integer x for which x square is congruent to minus 1 mod p. Okay, so here we are directly using the previous lemma. This means, okay, what does this mean? It means that the difference of x square and minus 1 is divisible by p. In other words, p divides x square plus 1. So it means there exists an integer integer c for which x square plus 1 is a multiple of p. Okay, now we can of course choose, I think I should have written this before writing it. Will it make any difference? Okay, let us just see. Now we want to choose this x wisely so that we can get something. We can of course choose x such that x lies between 0 and p minus 1. Why is that so? You see, if you are familiar with, of course you have to be familiar with congruences, otherwise you cannot understand this result. If you have a solution x for this congruence, say, then the solution is some integer that satisfies this congruence, and that particular integer can be replaced by the remainder when you divide the integer by p. That remainder will also be a solution to the congruence. In other words, what I am saying is this: if you divide x by p, say, you get kp plus r, where r is the remainder. Then if you substitute this here in the congruence, because it is a solution, what will you get? Kp plus r whole square is congruent to minus 1 mod p. If you expand this using the square formula, then you will get a term involving k square and a term involving k, and then you will get r square. Those first two terms can be removed because they are congruent to 0 modulo p. So you will be left with r square congruent to minus 1 mod p. And that's why always you can use an integer that lies between 0 and p minus 1. That is because the remainder satisfies these inequalities. Okay. The size of x can be further restricted to this. X can actually be chosen to be less than or equal to p minus 1 by 2. Is it that p minus 1 by 2? No, I think there is a mistake here. It is not p minus 1 by 2. It should be p by 2. Okay. Excuse me. Because if x is greater than p by 2, suppose the x that we have chosen here turns out to be greater than p by 2, then we can replace this x by p minus x. Because if x is greater than p by 2, then p minus x is less than p by 2, and p minus x of course is greater than 0. Why? Because this is this is already there. This is strictly less than p, so p minus x is greater than 0, and p minus x satisfies the congruence x square congruent to minus 1 mod p. In fact, if you are familiar with the theory of quadratic congruences from number theory, you already know that every such congruence has exactly two incongruent solutions, just like every quadratic equation has exactly two roots, something like that. One of them, if one of them is x, the other is p minus x. Okay, so if either x is less than or equal to p by 2, and if it is greater than p by 2, then p minus x is less than p by 2, and that also satisfies the congruence. So in any case, we can assume that x is less than or equal to p by 2. Okay, now what does this inequality imply when we apply that here in this equation? Now Cp, which is x square plus 1, becomes less than, since x is less than p by 2, so this is less than p square by 4 plus 1, and this turns out to be less than p square. Why? Let us see why. What about this last inequality? If we subtract p square by 4 from both sides, we are left with 3p square by 4, right? And if we manipulate a little bit more, then we get this. Now since p is a prime of the form 4n plus 1, the least value of p is 5, and for that this inequality is clearly true, and for higher values it will be even bigger. So this inequality turns out to be true. Which implies if we cancel, or if we subtract by p, if we subtract both sides by p of this inequality, we then get this. So c is an integer that is less than p, and in fact you can see that c cannot be negative because p is positive, x square plus 1 is also positive, so c has to be positive. Thus c is a positive integer. Okay, we are saying c is positive. Can c be 0? No, it cannot be, because this is already greater than 0. Okay, so c is a positive integer less than p. Hence c and p are relatively prime, because you see their greatest common divisor is 1. That is because the only positive common divisor is 1. The only two positive divisors of P are 1 and P, because P is a prime number, and because C is less than P, P cannot divide C. So P cannot be a common divisor of P and C. So the only common divisor of P and C is 1, and that is the greatest common divisor. Now look at the situation. We have a prime P of the form 4n plus 1, and there exists an integer C for which we have this, and C and P are relatively prime. So that means we are in a position to use that lemma from the other video, that lemma 381, and conclude that P is a sum of two squares. Hence, thus, by lemma 381, there exist integers a and b such that P is equal to a square plus b square, and this completes the proof. Okay, this is an existence proof. It does not tell us what a and b are. It says that there is at least a pair of integers a and b for which this is true. Okay, and this result is due to Pierre de Fermat, the French mathematician, and this result can also be proved using elementary number theoretic techniques without using algebra or theory of Euclidean rings like this. However, that needs a lot of effort. We need a lot of effort to substantiate the result if we take elementary number theoretic approach. Instead of that, if we use theory of Euclidean rings, then we get the result somewhat with much less labor. And this also shows that Euclidean rings have, besides many other applications, this is one of the applications. So after this we are now going to see the exercises at the